In this video, we are going to talk about organic chemistry. So this is the first of a series of videos relating to organic chemistry. We will firstly discuss some of the concepts like alkanes, alkenes, alkynes, so as the simplest homologous series of hydrocarbons. And we'll also look at how to write empirical formula and its differences with molecular formula, semi-structural formula, and skeletal formula. We will also be having a look of different types of isomers, in particular structural isomers, positional isomers, functional isomers, and stereoisomers. So let's begin. So first, let's start with an overview of organic chemistry. So organic chemistry is a study of carbon-based compounds. And this exclude things like carbon monoxide, carbon dioxide, as well as some ionic compounds containing carbonates. Because for organic chemistry, what we are really looking at is we are looking at things to do with living life. And for carbon dioxide and carbon monoxide, they are considered as inorganic. So the whole study of organic chemistry is based on carbon. And carbon is really a very special element. So it is very abundant, but it also has some interesting properties that really makes this whole organic chemistry stuff alive. So first, let's look at some of the chemical properties. So carbon has 4 valence electrons. And this is really special because we know for most elements, they either have 1, 2, or 3 valence electrons. So it is really quite rare for some element to have 4 valence electrons. And we know that carbon has covalent bond. And because it has 4 valence electrons, carbon can form single bond, double bond, and even triple bond. So really a lot of flexibilities here. And another very important property is that carbon can bond with other carbons. So this really enables even more flexibility. So it can form chains and even rings. And it can also form covalent bond, not with carbon, but with other non-metal elements as well. So some of the examples include hydrogen, oxygen, nitrogen, sulfur, phosphorus, and also a class of elements called halogens. So this includes things like fluorine, chlorine, bromine, things like that. So they all belong to this same column on the periodic table. And because of this flexibility, carbon can be the basis of a huge range of compounds that's used in living organisms. So that's why we study organic chemistry, and that's why we study carbon, because it is really a very special element. The flexibility is really unbelievable. So the first topic let's look at is bond strength. So we know that covalent bond requires energy to break. And the amount of energy required to break this covalent bond is called bond strength. So if you require a lot of energy to break the bond, then this means the bond is very, very strong. So let's have a look of some of the bond strengths of different covalent bonds. So for this carbon to carbon triple bond, the bond energy, which is measured as kilojoules per mole, is 839. For carbon to carbon double bond is 614. For carbon to carbon single bond is 347. Carbon with fluorine has the strength of 453. Carbon with hydrogen has a strength of 413. So there are some interesting trends here. So as we move from single bond to double bond to triple bond, we can see that the bonds are stronger. And we move from something less electronegative, such as hydrogen, to something more electronegative, such as fluorine. We also have stronger bonds. But this have some unexpected additional properties. So in fact, although the carbon to carbon triple bond is much stronger than the carbon to carbon single bond, and precisely because of this reason, because the triple bond contains a lot of energy, this means the carbon to carbon triple bond is more reactive than the carbon to carbon single bond. So this is also an important property for you to remember. Now let's move on to the discussion of homologous series. So I already touched on this point in the first video when we talk about non-renewable energies. So a homologous series, the formal definition is a family of structurally related molecules with the same functional group. So this is really important. If something have different functional groups, it is not belongs to the same homologous series. And each successive member differ by CH2 group. So all the families we are going to look at today, which is alkanes, alkenes, and alkynes, they all belong to a different homologous series. So the chemical properties of homologous series are similar because they have the same functional group. And I think a very good way to understand functional group is to really look at this phrase in detail. Because it's called function group, functional group. It gives this homologous series a different function. And since everything in the homologous series have the same functional group, they should have similar function. And that's why the chemical properties are similar. But the physical property such as boiling point is not similar between compounds in the same homologous series. So it shows a trend. And the trend is as the length of carbon chain. So remember, each member differs by CH2. So CH2, 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 etc. So as the length of this carbon chain increases, the amount of dispersion force also increases, and hence the boiling point increases. So this is the trend, and this applies to alkanes, alkenes, and alkynes. So something with longer chains, such as petrol, would have a higher boiling point than natural gas. And we know this because petrol is a liquid at room temperature, but natural gas is a gas at room temperature. And the reason is because petrol has a longer carbon chain and thus a larger molecular size. And this would increase the amount of dispersion force. And this explains why the boiling point for petrol is higher than natural gas. So now let's begin our formal introduction of hydrocarbons. So we have touched on this idea when we talk about fields in the first area of study. But now let's look at them in great detail. So hydrocarbon is something that contains carbon and hydrogen only, so nothing else. So that's why it's called hydrocarbon. Carbon refers to C, hydro refers to hydrogen. The simplest hydrocarbon or the simplest homologous series of hydrocarbon is called alkanes. And remember this ane suffix, because from this we can actually tell whether it's single bond, double bond, or triple bond. So the alkane family are hydrocarbons with only carbon-to-carbon single bond. So only has single bond. And they are saturated molecules. So this means every carbon has 4 single bonds attached to it. And this makes sense, right? If you have carbon-to-carbon double bond, then it's no longer saturated because you do not have 4 single bonds, you have a double bond. So only if you have carbon-to-carbon single bond, it's saturated molecule. And it follows a tetrahedral arrangement. So one is coming out of the page, one is going into the page. And the bond angle between them is 109.5 degrees. You can obtain this by divide 360 by 4. So each carbon is the central atom, and this is the angle. This topic is covered in year 11 chemistry. So it's called tetrahedral. It's not really assessed on the chemistry exam, but it's good information to know. And when we are talking about homologous series, we need to deal with something called prefixes. And prefix basically tells you the number of carbon in the chain. So we know that petrol is octane and it has 8 carbons. So we really need to know the rule of this prefix in order to work out how many carbons we have in the carbon chain. And this part is really heavily assessed in the exam. So let's draw out a table. So number of carbons versus the prefix. So when you have only 1 carbon, so for natural gas, we know it's called methane. So the prefix is just METH. When you have 2 carbons, it's ETH. So for alcohol, it's called ethanol. So because alcohol we know has 2 carbons, it starts with ETH. And this is exactly what we would expect based on this table. When we have 3 carbons, is prop. 4 carbons is bute. The liquefied petroleum gas contains a mixture of propane and butane. Propane, as you can tell from this table, contains 3 carbon atoms. Butane contains 4 carbon atoms. 5 is called pent. 6 is hex. 7 is hept. 8 is oct, so octane. 9 carbon is NON, and 10 carbons DEC. So the last 3, so that's all you need to know for the chemistry exam. You will only ever be asked up to 10 carbons. So the last 3 I think are easier to remember. So it's something like October, November, December. So that's the last 3. And the rest, I think you need to memorize them somehow. I really don't have a very good way to memorize this. Maybe for ethanol, it's easier to remember because it's alcohol. But for the others, come up with a way to remember it. And the general formula for alkanes is CnH2n plus 2. So if we have 1 carbon, we should have 4 hydrogen. And this makes sense because for methane, let's verify this rule. You have CH4. And for ethane is 2 carbons. You have something like this, C2H6. And 2 times 2 plus 2 is 6, and so on. So this is the general formula. And now let's draw pentane. From this prefix pent, let's go back to our table, PENT. So we need 5 carbon in our carbon chain. 1, 2, 3, 4, 5. Because it is ANE, we know it only contains carbon-to-carbon single bond. And then let's fill in the gap and draw the hydrogen atoms. So what is the trick of drawing hydrogen atoms? So if you look at each carbon in isolation, it should only be connected to 4 different things. So for this carbon, it's connected to 3 hydrogens and 1 other carbon. For the carbon number 2, is connected to 2 hydrogens and 2 carbons. So a rule of thumb is that for the carbon in the middle, you have 2 hydrogens attached, because towards the left and towards the right, it's connected to another carbon. And for carbons at the end or beginning of the chain, because it is not connected to carbons on the very end, it is connected to 3 hydrogens. So that's how you remember, or that's how you draw alkanes. And because let's count how many carbon we have. We have 5 carbons already. For hydrogen, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. We have 12. You can, of course, also use the general formula. So we have CnH2n plus 2. So C5H 2 times 5 is 10 plus 2, which is C5H12, as you would expect from drawing as well. And for something with the formula C5H12, it doesn't necessarily need to be pentane. So it can look like something else. So this is what I call it as isomers. So although it has the same amount of carbon and hydrogen, it can look different. So maybe let's draw a different example, but with the same chemical formula, C5H12. So now we only have 4 carbon in the carbon chain, but we can branch out another carbon, and we can fill in the hydrogen here. Because this is also and carbon, it is attached to 3 hydrogens. You can have something that looks like this. And if you count the number of carbons, 1, 2, 3, 4, 5, and hydrogens, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, also has the formula C5H12. But as you would appreciate, it should no longer be called pentane, because it doesn't have 5 carbons in the main carbon chain. So what do I mean by the main carbon chain? So it is the longest carbon chain you can draw without lifting your pen. So for this one, I can reach 5 carbons without lifting my pen. For the second one, 1, 2, 3, 4, I can only do 4. Or I can do 1, 2, 3, 4. I can only do 4. It is not possible to connect the 5th carbon. So the main chain should have the name built in, because there's only 4 carbons in the chain, in the longest continuous carbon chain. So what is this thing called? So whenever something branch out, when you have only 1 carbon branch out, you also start with mass. So starts with the prefix, and you add the suffix YL. So it is called methyl group. When you have 2 carbons branch out, it's called iso group, iso group. So that's the naming convention of the group that branches out. And we also need to assign this methyl group a position, because maybe it can be located here. So how do we assign the position? There are actually 2 ways to do it. So the first way is incorrect, and the second way is correct. So we can name the longest continuous carbon chain. So this is 1, 2, 3, 4. And because this methyl group is on position number 3, should we call it 3 methyl? So this is a problem, because we can also assign the number in the opposite order. We can assign this carbon number 1, this carbon number 2, this carbon number 3, this carbon number 4. So based on this method, we should call this 2 methyl. And in fact, this 2 methyl naming is correct. We want to keep this number as low as possible. So we don't want to make this too big. And so it has the second position on the carbon atom, on the carbon chain, and it is a methyl group. And we know the longest carbon chain is a butane. Why is it butane? Because it has 4 carbons in the longest carbon chain and only has carbon-to-carbon single bond. So the name of this species is called 2-methylbutane. In fact, you can even drop this number 2 and call it methylbutane directly, because there's only really one way the methyl group can be named. So if you place the methyl group here, you would still get 2-methylbutane. But if you attach the group to the end, you would get pentane. So that's why we can drop this number 2, because there's only one way the methyl group can go. But if there are multiple ways the methyl group can go, we need to assign them a position. So this is a little bit complicated, but in the next video, we are going to do some practice on naming hydrocarbons. And these 2 molecules are called structural isomers because they have the same chemical formula but different structure. So that's why it's called structural isomers. We can also have something called alkenes. So ENE. And this is something with carbon-to-carbon double bond. And because it has carbon-to-carbon double bond, each carbon is no longer connected with other carbons with 4 single bonds. So it is unsaturated. This means there is carbon-to-carbon double bond present. The general formula is CnH2n. So if you have C6, you should have 12 hydrogen atoms. So this one is easy. So whenever you add an extra bond, you take away 2 hydrogen atoms. So for the triple bond is CnH2n minus 2. So that's the general rule. So now let's draw one of the alkenes. But2-ene. So let's have a look and trying to understand what this thing is saying. So but, when we refer back to our previous table, corresponds to 4 carbon atoms. So this 4 carbon. And ENE means carbon-to-carbon double bond. This number 2, which is before ENE, means it is in position 2. So the first thing you need to do is to draw the main carbon chain. So 4 carbon atoms. And you need to name each carbon atom. So this is number 1, this is number 2, number 3, number 4. And we know that the double bond is in position number 2. So in this position. You can also go from right to left. Doesn't make any difference. And then you fill in the hydrogen to complete the gap. Remember, each carbon can only ever be connected to 4 bonds. And for carbon number 3, we can see there are 2 bonds at the left, 1 at the top and 1 at the right. So 2 plus 1 plus 1, 4. So it cannot have another hydrogen there. And similarly for the second carbon, only connected to 1 hydrogen only. So compared to something with single bond, it has lost 2 abilities to connect with hydrogen. So that's why the general formula have 2 less hydrogens. So this is how do you draw build 2 ENE. So does build 3 ENE exist? So maybe let's draw them and then see whether this exists or not. 1, 2, 3, 4. So the double bond is here. Because the end carbon is connected via a double bond, it loses the ability to connect with one other hydrogen. Hydrogen. So although you can still draw build 3 ENE, but this naming is incorrect. Because we should always remember we need to keep this number as low as possible. So instead of going from left to right, we should name from right to left. So this is number 1 carbon, number 2, number 3, number 4. So this should actually be called build 1 ENE. Because we want to make the name as small as possible. And the general formula for this, if you count the number of hydrogens, is C4H8, which should be correct based on our general formula. So now let's name some of the alkanes. This one is a little bit tricky. So you might say, oh, you have made a mistake. Why there's no hydrogen connected to this carbon? Well, if you look at the 2 double bonds on the left, you have 2 connected. And when you look on the right, you also have 2 connected. So it's actually already have 4 bonds already. So we do not need to connect this carbon with hydrogen anymore. So now let's try to name this compound. The first thing you need to remember is always to count the number of carbon atoms in your chain. So we have 1, 2, 3, 4, 5, 6. 6 carbon atoms. So when you go back to the table, 6 is hex, so it should be something to do with hex. There is no branching out, so there's no things like this methyl group. So we shouldn't add anything in front of this hex. But the problem is we have 2 double bonds. So the first thing to deal with is how do you assign the position. We can assign from left to right. In this case, the double bond would have the position of carbon number 4 and carbon number 5. But we want to keep the number as small as possible. So we should name from right to left. So this is carbon number 1, this is 2, this is 3, 4, 5, 6. So the position should be hex 1, 2. Do I still call it ENE? This is not correct because we have 2 double bonds. So for 2 double bonds, we call it di-ene, so Di. So if we have 1, we just call ENE. We have 2, it's called di something. 3 is tri something. 4 is called tetra, ENE, for example. If you have something like this, it is built 1, 2, 3, tri ENE. So now let's look at easier example. So what is this called? You should name from left to right because this gives a lower number. So you have 5 carbon in the main chain, so it's pent, and the double bond is in position number 2, so it's pent 2 ENE since you have a double bond. Now let's look at the last homologous series we are going to look at today, so alkynes. So alkynes have carbon-to-carbon triple bond. It is also unsaturated, so only the carbon-to-carbon single bond is saturated. The general formula is CnH2n-2, since we lose 2 hydrogens for every additional bond. So let's name this molecule. So you have 3 carbons in the chain. Should be prop something. And the triple bond is in position number 1 if we count from left to right. And we want to ensure the number is as small as possible, so we really want to count from left to right. So it's prop 1, 1. But this naming is incorrect, because if the triple bond is here, it should be still called prop 1 YNE. So there's only really one position the triple bond can go, which is attached to the first carbon. Because there's only one possibility, and we do not need to give this numbering anymore. The numbering is there to help people who are drawing the diagram know where to put the triple bond. But if you only have one possible location to go, you don't need to do this extra step. So you want to keep things as simple as possible. So always checking that when you are doing your exam. If you only have one possible choice, then do not put or assign this position number. So let's draw hex 3 YNE. So when you go back to the table, hex is 6 carbon molecules. So 1, 2, 3, 4, 5, 6. And we want the triple bond to be in carbon number 3. 1, 2, 3. So this should be the position of the triple bond. And you just fill in the hydrogens. Sorry, this carbon should not be connected to any hydrogen because it already has 4 bonds. So that's the hex 3YNE. And the general formula C6H10. So 6 times 2 minus 2 is equal to 10. So now let's look at really one interesting molecule called benzene. So the chemical formula for benzene is C6H6. And it looks like this. So this one is a little bit difficult to draw. Because it should look like a circle. And there are 6 hydrogen atoms and 6 carbon atoms. But if you look at this diagram, you see one problem. Each carbon is only connected to 3 different things. So for example, this carbon is connected to 2 other carbon and 1 hydrogen. So there should be 1 valence electron left. And that's because each carbon in benzene has a delocalized electron. So the delocalized electron is shared between all carbons in the ring. Benzene is called aromatic molecules, because it usually have a distinct smell, and it can sometimes be represented as this. So the circle represents the localized electrons. So now let's look at how to write formulas for organic molecules. So there are 5 different formulas you are required to know or to draw for organic compounds. So the first one is empirical formula. So it is the lowest whole number ratio of atoms in a molecule. The second one is called molecular formula. So this is the actual ratio of elements in a molecule. The third one is the semi-structural formula. So it represents the arrangement of the atoms. So for example, if you have something like butane, you know that the molecular formula, which is the actual ratio, is C4H10. And the empirical formula, so this is the molecular formula. The empirical formula is the lowest whole number ratio. So you can actually divide this by 2 to get the lowest ratio, C2H5. So this is the empirical formula. And this does not actually correspond to any compound. It's just the lowest ratio of atoms in the molecule. So if you want to draw something with formula C2H5, I don't think it's very possible. But neither of molecular formula or empirical formula tells you what the structure of butane looks like. But the semi-structural formula looks like this. So this is essentially a condensed version of the actual structure. So this is CH3, CH2, CH2, CH3. So whenever you see something like this, you can draw out the structure very easily. Whereas for something like C4H10, you can really draw something like this and still be correct. But they actually have different semi-structural formula. For this one, it's CH3, CH, so CH3, CH, with a bracket CH3, and then CH3. So this part, the branched out part, has a bracket. And whenever you see something like this, you can immediately draw out the full structure. So that's why it's called semi-structural formula. So it helps you to draw the structure without actually drawing it. But if you look at the molecular formula alone, you really can't tell which structure or which isomer you are referring to. We also have something called skeletal formula. So this one is really used to save time. So each bond is represented by a line. So the butane actually looks like this. So at each end, there is a carbon here. And for each of this turning point, you also have a carbon. And the carbon, you just use the hydrogen to fill in the gap. So this skeletal formula is really useful when you have a very long chain. So if you have 20 carbons, it's very easy to draw the skeletal formula. So name this compound. If you draw it in this way, it may look very interesting. Looks like a logo of Mercedes. So how do you name this compound? Remember, each end corresponds to a carbon. And the middle is also a carbon because it's actually a turning point. And then you just fill in the gap. So 3 hydrogen here, 1 hydrogen here to make it 4 bonds. Here we also want 4 bonds. So we identify the longest continuous carbon chain. And so this one branches out. So it is methyl because you only have 1 carbon in the branch. Propane. You don't need to add number 2 here because there's really only 1 position for this to go. So that's how you interpret and draw structural or skeletal formula. The last type, the 3D structural formula. So basically the full formula of this compound. Be very careful which type of formula you write out because in the exam they will specify which formula they want you to use. Sometimes they ask you to state the empirical formula. In this case, for the case of butane, you need to say C2H5. Molecular formula, you write C4H10. Semi-structural, you write CH3, CH2, CH2, CH3. Skeletal formula, you draw something like this. For the 3D formula, you just draw as normal. So let's look at one complicated example. So you have this thing going on here. You also have this. So really complicated looking. But don't be afraid. Always fill in the gap first. So you have carbon on the end. You have carbon at every turning point. And then you draw out the hydrogen. I will not label hydrogen this time to save some time. So this carbon has 3 bonds, so we add 1 more hydrogen. Hydrogen, 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 hydrogen. So now let's identify, so first let's look at the molecular formula. So this is the actual number of carbon and hydrogen in this compound. We have 1, 2, 3, 4, 5, 6, 7, 8 carbons and 18 hydrogens. You can also use the rule because it only has carbon to carbon single bond. 8 times 2 is 16, 16 plus 2 is 18. So you can also use the rule to figure out the molecular formula. The empirical formula, you divide this maybe by 2 first. C4H9, and you cannot divide this with whole number ratio anymore. So this is the empirical formula. So now let's write the semi-structural formula. To do this, we need to find the longest continuous carbon chain. So 4, 5. 1, 2, 3, 4, 5. So it looks like it has 5 carbon as the longest chain. So you can use this chain. Alternatively, you can also use this chain. Really doesn't make any difference. So let's stick with the horizontal chain. I think it's easier to see. So we start with CH3 and then we have CH. And we have 1 methyl group, which is written as a bracket. Then we move on to this carbon, which is also CH. But this carbon is connected to the ethyl group. So it's CH2CH3. And then let's move on to this carbon, CH2. And lastly, this carbon CH3. So this is the semi-structural formula. And then the structural diagram, or the 3D structural diagram. You just copy this out. Just copy down CH3, CH, CH3, CH, and then CH2, CH3, CH2, CH3. So really not too hard if you just follow the procedure. Fill in the gap and then identify the longest continuous carbon chain. And then you can basically do whatever you want. And you can arrive at the correct answer. So having said all of that, I want to make the idea of isomers more concrete. So the structural isomers. So structural isomers refers to molecules with the same molecular formula. But different arrangement of atoms. So you can have something like this, or you can have something like this. So they all have the same amount of carbon and hydrogens, but different arrangement. So one is a straight line, the other one has a branch. So this branching is only possible if you have more than 4 carbons. 4 or more carbons, I should say. So for 3 carbons, if you move this carbon here, you still have 3. So there's really no way you can create a structural isomer. If you have 4 carbons, you can put 1 carbon here to get a structural isomer. And if you have more than 4, you get a lot of different flexibility. So this branching out is called alkyl group. So that's why everything ends with YL. So you have the methyl group, butyl group, ethyl group, things like that. So this is called the chain isomer. For example, pentane C5H10 has 3 structural isomers. So let's have a look. Let's see if we can draw all of them out. So the first one is very easy. Say just this. I would not write the hydrogen out to save some time. The skeletal formula is something like this. Another one, let's use one branching. Put it here. So if you recall with the naming convention, this is methyl butane. You don't need number 2 here since there's only one possibility. You can also branch out further. So you can do something like this. So this one is dimethyl propane. It's called di because it has 2 methyl groups, or the 2 branched out groups. You really don't need to put the number here, but if you do, it's called 2,2-dimethyl propane. because both methyl group is located on number 2. But really there's only one possibility, so you don't need to put a number here. So the side chain, as I have mentioned many times now, is called the alkyl group. So it's so the naming convention is just whatever prefix you have based on the number of carbon, you add YL. So 1 carbon is methyl, 2 carbon ethyl, 3 carbon propyl, things like that. It's very rare for you to go for more than 3 carbons because you really need a very long carbon chain for a branch to have 4 or 5 carbons. So if you have one alkyl group, it's just methyl something, so you don't have any prefix. If you have 2, it's di something, depending on how many carbon you have. Maybe for this example, you have dimethyl. If you have 3 alkyl groups, you have tri something. 4, you have tetra. And it's really rare for you to go more than 4, so I won't cover those in this video. So this is the structural isomer. We are already very familiar with this since we have already done a lot of practices. The positional isomer. So this is a different location of the functional group. We will really discuss this in more detail when we have a formal introduction of functional group. But this is one example. So this is the propan 1O. So the hydroxyl functional group is located at the very end. But it's still possible for the hydroxyl group to be here, to be at the middle. So it's propan 2O. So that's what I mean by positional isomer. So different positioning of the functional group. More on this later. So how do you determine all the structural isomers present in the system? So if you have double bonds, so maybe some of the method. So if you have double bond or triple bond, you can move them around and it shouldn't make any difference. So if you have something like this, you can move around to here. And in this way, you can get some structural isomers. So this is the first way you can do it. The second way is to move around the functional group. So as in this example, you move the functional group around. You also can move the alkyl group. So maybe if you have something like this, you can move it to here. And then you get some additional structural isomers. You can also remove, so if you have 5 carbons, you can remove this 1 carbon and then put it at the middle to form additional structural isomers. And if you have something very special, if you have, for example, chlorine here instead of hydrogen, you can move the chlorine around to get additional structural isomers. So that's some of the techniques for you to determine different structural isomers. The key idea is if you have some useful features like double bond, triple bond, or connection with elements other than hydrogen, move them around. If you have a very long carbon chain, cut off the carbon at the end and see if you can put that carbon as an alkyl group somewhere in the middle of the chain. So that's the strategies for you to find all different structural isomers. So now let's move on to a different type of isomers. It's called stereoisomers. So this is a different arrangement in space. So we now are thinking in 3D. And this, the first one is called geometric isomers. And this applies to double bond only. So in this CC double bond, the bond itself cannot rotate. So the relative position of each element connected to this double bond is fixed. So you can have something like this and something like this. So although it's all 2 carbon, 2 hydrogen, 2 chlorine, you can get different arrangement because this carbon to carbon double bond is fixed in place. You cannot move things around. So that's why we get isomers. We lose this flexibility. So we introduce more possibilities for different arrangement in space. So here, so this one is called trans. Means opposite. So you might heard of the term trans fat. And this refers to this kind of arrangement. So the two same elements are located on the opposite side of the carbon-carbon double bond. And this is called the cis, means it's on the same side, or at the bottom. And this gives them different characteristics. So firstly, let's write down the name of those two species. So this is called cis 1,2 dichloro ethene. So it's di because we have 2 chlorine atoms. Chloro is just a special name. So whenever you have halogens, so whenever you have something like fluorine, chlorine, bromine, in the case of fluorine, it's called fluoro. Chlorine is called chloro. Bromine is called bromo. So that's some of the naming convention you need to remember. And for the double bond, also remember cis is at the front. The naming is exactly the same, except we have trans at the front. Trans 1,2 dichloroethene. And they have different chemical properties. So for this one, so for the cis molecule, it is difficult to pack closer because each side they have different shape. It's not, it's unlike the trans, which is more easy to pack. But the trans, if you look at the distribution of charge, chlorine is partial negative, and you have partial negative on both sides. So for the trans, you have a symmetrical distribution of charge. So this really makes it less polar and reduces the boiling point due to lower intermolecular force. But for the cis molecule, you can see there's a divergence in charge on both sides. So you get a more stronger dipole-dipole interaction. So this is reflected in the boiling point and melting point of these two chemical species. So the melting point for the cis is negative 81 degrees. For the trans is negative 49.4 degrees. So the trans has higher melting point because it can be packed closely. For the boiling point, we get a different scenario. So the cis has 60.2 degrees, trans 48.5 degrees. Because for the boiling point, we are overcoming this intermolecular force. And we know that cis has stronger intermolecular force because it has an unequal distribution of charge. So the chlorine side is partially negative, the hydrogen side is partially positive. So you have a stronger dipole-dipole interaction. And boiling point is the point you overcome the intermolecular force. So that's why it has a stronger boiling point. But for the melting point, we really only look at how closely or how easily you can pack those two chemical species. So we can also perhaps do another example. So draw the cis-trans isomer of pent2-ENE. So the cis isomer is everything on the same side. So I think a good way to draw this is to actually draw the double bond arrangement first and then draw the rest of the carbon. So because we know we have double bond, so we still have one hydrogen left. So because they have a cis arrangement, the hydrogen should be on the same side. And then you draw the rest of the carbon chain. So this is the cis configuration. For the trans configuration, you draw the hydrogen first. You force the hydrogen to be on the opposite side. And then you draw the rest of the carbon chain. So this is the trans configuration. Really easy to draw if you started out from drawing the double bond and then draw the hydrogen in cis or trans arrangement, and then you fill in the rest of the carbon chain. So this is one type of stereoisomers. The second type of stereoisomers is called optical isomers. So we know that we have this tetrahedral arrangement of carbon atom. So if this has 4 different types of things attached to it, so if you have species 1, 2, 3, and 4, different atoms or groups of atoms connected, it cannot be superimposed. On its own mirror image. So consider those two examples. So these two things are mirror image of each other. But if you actually try to rotate, imagining turning the first one to the orientation of the second one, if you turn this 180 degrees, so you get, so the 4 becomes here, and then you have 3 at the back, 2 at the front, which is different arrangement as its mirror image. So the mirror image has 2 at the back and 3 at the front. So whenever you have 4 different things attached to this carbon atom, it is called chiral. So it has a left hand and a right hand. And if you look at your right hand and left hand, you cannot superimpose them onto each other. They are actually different, just mirror image of each other. So this carbon is called the chiral center. So the central carbon atom. And because they are called optical isomers, optical has always have something to do with light. Because the polarized light interact with those two isomers differently. So you can use this property to distinguish between those two isomers. So actually the molecule and its mirror image, they are called enantiomers. So this is molecules with its own mirror image. So this is also a special name you need to know. And that's really, I think, everything you need to remember about this optical isomer. So whenever you have four different things connected, you get a chiral molecule. And you have two different mirror image of each other called enantiomers. So one example is this: CH3, CHOH, CH2, CH3. So immediately you can know that this carbon is the chiral center, because it's connected to CH3, which is group A hydrogen group B, OH, which is different from CH3 or H group 3, and also CH2 group 4. So let's draw them out. So as you can see, it's really connected to four different things. So this is a chiral center. You use this asterisk to label it or to emphasize it is a chiral center. So this is actually a chiral molecule. And we need to see how this molecule interacts with light to determine which one it is.